So we're going to do an example problem that's going to allow us to use a lot of the information with conservation of momentum, conservation of kinetic energy, and also allows us to use angular momentum. So let's get a billiard ball table. And so I have this billiard ball table, and what's going to happen is you hit ball A, and ball A is going to come in and collide with ball B, but after the collision, it's going to go over here and hit with ball C, and A is ultimately going to hit at A prime on our billiard table. C is going to hit at C prime on my billiard table, and B is going to hit at B prime. All of these dimensions are in feet, so we have that, and we're told that we have an initial velocity of 10 feet per second, and it's traveling along this line of D. Now, this problem is going to be very important to look at how we are doing the various pieces of this problem and the diagrams. Because when we hit the momentum afterwards, ball B is going to have an X component and it's going to have a Y component. Ball C is only going to have an X component, but at the end, ball A has a Y component, but ball A started out with only an X component. We're told that all the balls have the same mass, which is going to help us out greatly. And we're told that we're on a frictionless surface and it's perfectly elastic. And we want to determine the velocity at A, B, and C after the collision. So things that we know the initial velocity. It's got a 10 foot per second magnitude. It's only in the X direction given our picture. We know we have conservation of momentum. But the fact that it's a perfectly elastic collision allows us to know that we can get conservation of energy. So let's look at the before and after of our collision. So before our collision, we have in the X direction, A is going to hit and it's going to finish with only a Y component. So at the very end, we've got the mass times the velocity of the B in the X direction. And then I have the mass of the velocity at C. In the Y direction, we've got no Y direction initially. We only have our velocity in the BY direction, and we have our velocity in the AY direction at the end. We can also use our angular momentum. So we've been given one equation, we've been given two equations, but we can use our angular momentum to give us a third equation. So without that conservation of kinetic energy, because it's a perfectly elastic collision, we can still get three equations here. But the problem is we've got four unknowns. We've got the velocity of the A unknown, we have velocity of B unknown, and we have the velocity of C unknown, but our velocity of B is unknown. It's both in the X and Y direction. So we're going to use our angular momentum. So our angular momentum before is going to be our lever arm, 2 feet. We've got the velocities going in that direction, so we're going to end up with a rotation in the negative direction. Similarly, at A, I've got my X direction I don't have to worry about because it's in the line with my origin. I only have to worry about the Y, so I want to have that. And so this one is going to give me my -7 times my velocity in the B direction, again, because this one is going in this direction down. I'm going to have a negative direction there. Now this one, I'm in the positive direction here. I'm at 8 feet away from my origin, so I'm going to have a positive rotation. And just like what we saw on the other side, I'm going to end up with a negative rotation. So I can get this, and remember my angular momentum is R times the mass times velocity. So what's going to happen to me here is I'm going to get my three equations, but I've only got four unknowns, so we're going to end up having to get another equation. So let's simplify this. Everything's got the same masses, so I can simplify these. I get my three equations. I get equation 1, equation 2, equation 3. And now we're going to have to use that conservation of kinetic energy for that perfectly elastic collision in order to get our fourth equation. So a couple things here. V is going to be, or V of B is going to be my BX squared plus my BY squared. I can put these into this, so I can have this. Remember, all the masses are the same. Everything has a 1/2 in front, so I can get rid of that. I can divide both sides by 1/2 and m, and I've got all of that taken care of. I can plug in the values that I know, and I end up with an equation that looks like this. Now I've got 4 equations, 4 unknowns, so I've got to solve it. Well, it turns out these are pretty easy equations to solve. So when I do that, there we go. We can do from equation 1, I can do it in terms of VC. I can do my equation 2, which allows me to plug into equation 3. So I get everything in terms of the velocity of the C ball. So now I plug all of that into my equation 4, and then it just becomes a math exercise until I get all the way down here to my quadratic equation. Well, when that happens, I ultimately need to get 2 solutions, and I'm going to get a solution of 5 feet per second, and I'm going to get a solution of 8 feet per second, but my velocity of A must be positive, so I'm going to be able to rule out that 5 foot per second velocity in this case for this particular problem. When I do that, I can plug all of this in, and I get my velocity of By is 4 feet per second. My velocity of Bx is 2 feet per second. Again, these are magnitudes. I have to go back and look at my picture so I can draw my velocity of my B in terms of its vector notation, so I can ultimately calculate its magnitude and its direction. So while this looks a little lengthy, it really isn't, and I can actually utilize these equations really, really well in order to solve the problem. So hopefully this gives you a good example, and we can go from there.